There you go, guys. Topic for the day. So given the fact that the word gas and gases is on the board twice, I think you can probably figure out what we're going to do for the rest of the year. But guys, let me explain to you why we're doing this. Maybe you don't understand. There's lots of great research that says that students are clueless about teaching. It's actually really interesting that people get this idea that they understand what it means to be a teacher from being a student, and it turns out the disconnect is huge. Doesn't matter. Anyway, so guys, as we as teachers sit down and figure out what are we going to do with the month of May, frankly, what we've got to do is find something that's short, that's concise, that isn't on the SAGE test, but actually provides the ability to get some things accomplished. So this is why we choose gases. There's actually two reasons. Guys, one of the reasons that Miss Call and I decide to wrap up the year talking about gases is because it's amazingly practical. Guys, what you're going to see is a lot of the things that you experience in your day-to-day lives actually comes down to some of the things you're going to learn even today. As a matter of fact, some of the things you're going to think about today, you're going to go, oh, I need to remind myself to think about that later when it's actually going on. You'll see. But guys, the other reason that we do this is because a good number of you are coming back for AP next year. And guys, my students just took their AP test on Monday. And as they're studying for the AP test, guys, not surprisingly, when we get within a couple weeks of the AP test, I stop directing the review process. I'm just like, guys, we have done as much as we can do as a group. I'm just going to get out of the way. I'm going to act as a resource, and I'm going to allow you time to address your particular misunderstandings as you're getting ready for the test. And guys, guess what the number one topic is that when my students are allowed to choose what they need to review, guess what the number one topic is that they realize they need more time with to get ready for the AP test? It's this stuff. Guys, this is the most complicated concept that we will talk about in AP next year. The gases unit is brutal. The reason is because just when you think you understand these things, you find out that you really don't understand them. So here's what we're going to do. We're going to spend 2 days on this. We're going to give you a general understanding of what gases are all about. It sets the stage for next year. And even if you're not coming back for AP, you're going to find out this is very practical. So guys, here's the way the day goes. First of all, we're going to remind ourselves what we already know about gases. Remember TOSOC and TOSVOC and all of that stuff? No, you don't. Okay. So I'll show you the picture from the notes back in when did we do this? January. I'll show you the notes from January. We'll remind ourselves what we know about gases. And then, guys, we're going to extend the conversation and talk about why are gases so hard to understand. Then we're going to talk about ideal gases, which is actually the solution to why are they hard to understand. And then once we understand what ideal gases are, we're going to talk about these things called the gas laws, which are the things that describe how gases behave when we start messing around with them. You get the idea? So here we go. So guys, don't write any of this down. But do you remember this day in class? Do you remember that? And we talked about solids, and they've got structure. They're high density, low energy. The particles just sit there and vibrate. And eventually, if we add enough energy, the structure collapses and they turn into a liquid. And we describe the liquid as being like a mosh pit as these things slam into each other. And eventually, we add enough energy to them that the intermolecular forces rip apart and they spread out into the container and they turn into this highly chaotic, very random, crazy business substance that we call a gas. Do you remember all of that? Well, guys, here's the trick. These things that we call gases are actually amazingly difficult to describe. if we wanted to talk about what is going on inside of a gas, guys, you would find out that it's actually almost impossible to describe how a gas behaves and what's going on inside of it. So the question then becomes, what is so complicated about a gas? Because liquids are actually really easy to describe. Solids are really easy to describe. So why would gases be so hard to describe? And guys, to answer the question, let me ask you this. What's wrong with this? If this is our picture of what a gas looks like, what's wrong with this picture? What are gases actually doing? They're not doing this. What are they doing? What's going on inside of a gas? What are we missing? So guys, if you could peer inside of a balloon, right? Blow up a balloon. If you could peer inside of a balloon, and if you could see the molecules of nitrogen and carbon dioxide and oxygen and all the gas that's inside of a balloon, if you could see those particles, what are they doing? Are they just sitting there? What are they doing? Do you know? They're moving around. How fast? Hundreds of miles an hour. And they're not just moving around at hundreds of miles an hour. What are they doing? They're slamming into the walls. They're slamming into each other. Guys, it is full-on crazy inside of a gas. And so I tried to find a video that would represent this, and I want to build one of these. I just found this first period today, and this was pretty good. So guys, if you want to know what it looks like inside of a gas, it does not look like this because the molecules are not holding still. So what are they doing? Well, guys, this is actually, I love this. I want one of these. It's pretty cool. I wonder how big this is, because those look like thumb screws that must be really small. But guys, this is actually a great model of what it looks like inside of a gas. Now, what you're going to see is this starts in real speed, and then for some reason, the guy that videoed it went to slow motion and then went back. But this is actually a great idea of what it looks like inside of a gas. That was horrible. Because this is really what it looks like inside of a gas. These molecules are slamming into each other. They're running all over the place. They're bouncing into the walls. They're bouncing into each other. And guys, this is chaos. Literally, mathematically, this is chaos. And chaos is impossible to describe mathematically. But guys, you got to understand, inside of a gas, it is very, very chaotic. And because it's chaotic, it's very hard to describe. So when you think of a gas, don't think of that picture that was on the first page. Guys, when you think of a gas, you need to be thinking of this, because it is nuts inside of a gas. So with that said, guys, this is where you then need to start taking notes. So what do we do about it? So guys, write down ideal gases, but don't write down the first bullet point. So the idea goes like this. Gases are crazy. They are random, they are high energy, and they're chaotic. And guys, this creates a problem. See, the problem is their behaviors are complex and almost impossible to describe mathematically. So guys, how do we deal with that in science? If we've got a system that's really hard to describe mathematically, what do we do if we can't deal with the system as it actually exists? And guys, this is where you want to start taking notes. Here's what we do. To address the complexity, what we do is we use a simplified model. Guys, it's a general principle in science. If you've got a system that you can't figure out, create a simplified system that gives you some general ideas about what the system is doing. So, this system, guys, gives us all sorts of advantages. You're going to find out in a minute it's called an ideal gas. But here's the way this works. Gases are really complicated. Because gases are really complicated, we need to create a simplified system. Now, the trick is this. This simplified system allows the math to become much more simple. So a simplified system allows simplified math. But here's the thing that's cool about the simplified math. the answers don't change very much. The answers that we get from this simplified system gives us about the same answers that we get with the complex system. So let's just say it this way. You guys are going to end up cramping up writing all this down. So to address this, we use a simplified system. This allows simplified math. But the simplified math, the simple math provides what would be a good way to say this? About the same answers. So the simplified math, how do you spell simplified? F-I-E-D, simplified. The simplified math provides about the same answers. Okay, so the idea here, guys, is that when we study gases, gases are really complex. Because the gases are really complex, they're hard to describe mathematically. So we use a simplified model. The simplified model lets us use simplified math, but the simplified math provides about the same answers as if we tried to deal with all the complexity. So the question then becomes, what is the simplified model? And guys, the answer is the ideal gas model. Let's even write it that way. I like that better. We're going to call this the ideal gas model. And guys, we're going to call this a model because ideal gases do not exist. You got to get that right up front. You may even want to write that down next to this so you don't forget. Guys, ideal gases do not exist. There's no such thing as an ideal gas. But ideal gases are very important because they allow us to study gases in a much more simplified way, and the simplified model works really well. So, what are the simplifications? What are the things that we do with an ideal gas to make it more simple so the math becomes easier? And guys, the answer is this. Ideal gases are gases that are composed of molecules with ... So what are the simplifications? And guys, here's the deal. Remember, these don't exist. There's no such thing as an ideal gas. And if you understand there's no such thing as an ideal gas, you're going to also understand that these simplifications are impossible. Like, for example, this. What is one of the two simplifications for an ideal gas? Ideal gas molecules have mass, but no volume. Mass, but no volume. What on stinking earth does that mean? What does it mean if something has mass, but no volume? We understand it's impossible, but what does that mean if you have mass, but no volume? What is mass? What does it mean if you have mass? You're stuff. You exist. But guys, what does it mean if you have no volume? You don't take up any space. Is that possible? Can you exist and not take up space? No. It's impossible. Guys, if something exists, it has to take up space. But in the ideal gas model, we are pretending that these molecules, and let's put it in layman's terms, that these molecules exist but don't take up space. And guys, that can't be. So what is the other oversimplification? And the other oversimplification is this, guys. Ideal gas molecules have no intermolecular forces. And you may be thinking to yourself, wait a minute, I thought that was the case. I thought gases don't have intermolecular forces. Do you remember when we said that? We said gases don't have intermolecular forces. So guys, let's talk about this really quickly to make sure you understand. So think of intermolecular forces like magnetic attraction between magnets. So guys, we understand that if these are both magnets, they attract each other and they stick, right? So this is what it looks like inside of a liquid. Oh, where'd it go? Where'd it go? Just boiled, sublimated. Okay, so this is what it looks like inside of a liquid, and these molecules are rubbing around on each other, and we get these things to boil, and they separate and the intermolecular forces break, right? But are these things still magnets? Sure, so what happens if I bring them together? They're still going to stick. So guys, we would say that when we separate these, they behave as if they're not magnetic, even though they are still magnetic, but they behave that way because we've separated them. And guys, gases are the same way. These molecules are moving all over the place, so for the most part, they don't attract each other. But what happens if gas molecules hit each other? And the answer is they stick only for a moment. So they go, wah, stick, let go, and they bounce off. Well, guys, in the ideal gas molecule model, we pretend like these things never stick even when they hit. So you may want to include that in your notes as well. They never stick to each other. And guys, understand that neither of these things is true. So the ideal gas model says this. Ideal gas molecules, this doesn't really happen. But guys, in the ideal gas model, these molecules are there, but they don't take up space and they aren't sticky. They never stick to each other, even when they hit. And guys, understand, both of those things are not true. We'll dig into this more next year. But guys, understand these things are not true, but pretending like they're true makes the math a whole lot easier. You get the idea? So here are the important things you need to understand, like for the test. So guys, why do we talk about ideal gases? You should be able to answer that question. Why do we do this? Why do we talk about ideal gases at all? Easier. Guys, real gases are complex. We can't study them. So ideal gases make the conversation easier. Do ideal gases exist? No, you need to understand that as well. We talk about them because they're easier. They don't really exist. And then, guys, you need to understand the two simplifications. One is the molecules have mass but no volume, so they're there but they don't take up space. And number two is they don't stick to each other even when they run into one another. You get the idea? Okay, so guys, with that as a background for ideal gases, now we're going to shift gears a little bit and we're going to talk about how can we change the way that gases behave. So it goes like this. This is the next topic in your notes. It's called STP. Remember when we talked about STP? Standard temperature and pressure, and we said that a mole of gas at STP has a volume of 22.4 liters. Remember that from a long, long time ago? So guys, you learned that a mole of gas has a volume of 22.4 liters at STP. And some of you ask, what is STP? And I said, don't worry about it. Well, guys, today we're going to worry about it. We're going to talk about STP. Now, don't write this down, but here's why we care. In order for us to understand gases, we've got to control the factors that change the way a gas behaves. So what are those factors? Well, those factors are temperature and pressure. If you change the temperature or pressure of a gas, it changes the way it behaves. So, and this is where you need to start taking notes, we then need to establish standards. Standard temperature and standard pressure. So guys, we're going to talk about them one at a time. We're going to talk about what is standard temperature. Then we're going to talk about what is standard pressure. Then we're going to talk about the gas laws, and then you're going to have a pretty good amount of time to get your homework done. So guys, let's do standard temperature first. What is standard temperature? Standard temperature is 0 degrees Celsius or 273 Kelvin. So guys, which one is it? Is it 0 degrees Celsius? Or is it 273 Kelvin? Both, because those are the same temperatures. Because what happens at 0 degrees Celsius? Water freezes, right? So guys, water freezes at 0 degrees Celsius. Water also freezes at 273 Kelvin. These are the same temperatures. And guys, one of the things you're going to find out is you've got to convert between the two. So here's the conversion. All of the math that we are going to do in this unit has to be in Kelvin. So guys, when you're given Celsius temperatures, you just need to add 273 to it, and that converts it to Kelvin. Are y'all caught up with me? You okay? So guys, I'm going to switch the slide over to a picture for just a minute. I want to introduce you to the idea of Kelvin, the Kelvin temperature scale. So you don't need to write any of this down, just check it out and I think it'll make sense. So guys, we're going to do a comparison between the Fahrenheit, Celsius, and Kelvin temperature scale. And we're going to look at the boiling point of water, the freezing point of water, and then absolute zero. Now guys, we've talked about absolute zero before. What happens at absolute zero? Literally, what happens at absolute zero? Nothing. Because guys, you understand that temperature measures speed, right? And even in frozen water, the molecules are still moving. They're locked in place, but they're still moving. If we cool it down to absolute zero, the molecules stop moving. Now guys, have we ever been to absolute zero? No, we've been within 1/10,000,000th of a degree, but we will never get there. It's impossible. You can't get to absolute zero. We're going to actually measure absolute zero in lab on Monday, but guys, it's impossible to get to absolute zero. So with that said, let's talk temperatures. So guys, do you know? Let's start Fahrenheit just as a reference. What temperature in Fahrenheit does water boil at? Do any of you know? 212. Do any of you know how they came up with 212? I'll tell you in a minute. Guys, what temperature does water freeze at in Fahrenheit? 32 degrees Fahrenheit. So let me explain to you the Fahrenheit scale. I just learned this year. So guys, this is how Lord Fahrenheit came up with his scale. He needed a 0 point and he needed a higher temperature, a 100 degree temperature point. Remember, this was 200 years ago. So here's what he did. He said 100 degrees, instead of being the temperature that water boils at, he said that 100 degrees was the temperature of his body. Now guys, what is body temperature in Fahrenheit? Do you know? 98.6. He was off by a little bit, but he said 100 is going to be body temperature. He was off by 1.5 degrees, but he said 100 is body temperature. And then for 0 degrees, he didn't use the freezing point of water. He used the freezing point of salt water. And remember, adding salt to water drives the freezing point down. So in the Fahrenheit scale, 100 was body temperature, 0 was the freezing point of salt water, and that's how we got 212 and 32 for being boiling and freezing for water. Then guys, in the Fahrenheit scale, absolute zero is about 460 degrees below zero. That's relatively chilly. Okay, so now let's go to the Celsius scale. This makes a whole lot more sense. What does water boil at? 100. What does it freeze at? 0. And on this scale, absolute zero is 273 degrees below zero. Get the idea? Okay, so now let's do the Kelvin scale. And guys, here's the trick. The Kelvin scale and the Celsius scale are exactly the same scales. The only difference is the 0 point. In the Celsius scale, the 0 point's the freezing point of water. In the Kelvin scale, the 0 point is absolute zero. That's the only difference. Guys, a Kelvin degree and a Celsius degree are exactly the same size. So if that's true, and if the only difference is the 0 point, what temperature does water freeze at in the Kelvin scale? 273. And what temperature does water boil at in the Kelvin scale? 373. So you ready for a deep question? What is the only thing a Kelvin temperature can't be? In theory, it could be 0. What can't it be? Negative. You can't have negative Kelvin temperatures because you can't go below absolute zero. So guys, what you're going to find out is in this unit, we are going to use Kelvin temperatures rather than Celsius temperatures because Kelvin temperatures can never be negative. You get the idea? But they're exactly the same as Celsius. You good? Okay, so guys, let's go back here then, and there's one more thing you need to include in your notes relative to standard temperature. At 0 Kelvin, there is 0 motion. And guys, that becomes important when we study gases. So that's standard temperature. So now guys, let's do standard pressure. So standard temperature is 0 degrees Celsius. Standard pressure, this is a little wishy-washy, standard pressure is the pressure at sea level on an average day. So guys, let's talk about air pressure. Why is there air pressure? Do you remember? What happens when you look up? Remember that idea? You are looking up through miles and miles and miles of air, and that air is pushing down on us, and it creates air pressure. Now guys, the question is this: how hard is that air pushing down? Well, let me see if I can put it in perspective for you. Have you guys all filled the tires on your car, like pumped up the tires on your car, and you put the pressure gauge on your tires, and like I just spent way more money than I wanted to and bought tires for my pickup a couple days ago, and I now know that the tires on my truck need to be inflated to 35. 35 what? What are the units when you inflate your tires? PSI, which stands per pounds per square inch. So inside my truck tires, for every inch of surface area, there's 35 pounds of force pushing out on my tires, and that's what supports my truck. So guys, with 35 as a frame of reference, how much pressure is the air pushing down on you at sea level on an average day? The answer is about half. It's actually 14. You don't need to write this down unless you want to. You don't need to know it. Guys, standard pressure is about 14.7 psi. So it's about half the pressure that's inside your car tires. But guys, that's not the unit that you need to know. We are going to talk about air pressure in two other units that you've probably never heard before. One of them is atmospheres. And standard pressure is defined as 1 atmosphere of pressure. We'll talk more about this later, but guys, the unit that you actually need to know, you guys have all heard of Pascal's triangle? Same guy. Turns out Pascal was not only a mathematician, he was also a chemist. And he actually measured, for one of the first times, air pressure. And we give him credit for that by naming our unit of pressure after him, which is called the kilopascal. And so guys, our unit for pressure, for standard pressure, is 101.3, what are called kilopascals. Okay, so as you're catching up, here's what we know. Gases are tricky. They're hard to study because they're so chaotic. Because they're so chaotic, we use a simplified model. What do we call the simplified model? The ideal gas model. Why do we use it? It makes the math easier. What are the oversimplifications? 1, the molecules are there, but they don't take up space. And 2, they never stick together. So now that we understand that, we now drew some lines in the sand, and we said temperature and pressure changes the behavior of gases, so we need standards. Standard temperature is 0 Celsius or 273 Kelvin. Standard pressure is 101.3 kilopascals, which is the pressure at sea level on an average day. You guys all caught up? Okay, so now guys, we got to do this. We are now going to talk about what happens, and this is how we're going to wrap up the day. We are now going to talk about what happens if we change the temperature or the pressure of a gas. How does it behave? Now guys, here's the trick. You already know this stuff. You ready? Watch my hands. If this is a balloon, and if we heat it up, what does the size of the balloon do? You guys all understand that? And what happens if we take a balloon and cool it down? Believe it or not, that's actually a law. and it's named after a person named Charles. You get the idea? Heat up a gas, it gets bigger. Cool down a gas, it gets smaller. You already knew that. We're just going to give it a name. Now, guys, what about this? So, all right. So when you were little itty bitty, right, you guys all had stuffed animals. Some of you still do, which is fine. But guys, you all had stuffed animals, whether you were a guy or a girl. It could have been a dinosaur. It could have been a bunny rabbit. Doesn't matter. Mine was a duck, and I actually still have the duck. And I used to, when I was a little kid, chew on the duck, and I still have the duck, and there's actually holes in the duck from where I used to chew on it. I was a weird child. But guys, when you're a kid, if you've got a stuffed animal, so imagine you've got a big old stuffed animal, and you're like lonely and you're sad, and you curl your arms around the stuffed animal and you squeeze it. What happens to the size of the stuffed animal? Does it get bigger or smaller if you squeeze it? It gets smaller, right? So guys, what we know is that if we increase the pressure on something, it gets smaller. And then what happens when you let go of the stuffed animal and you decrease the pressure? Well, it gets bigger again. Guys, that's all you're going to learn. That's it. We're done. Do you want your homework? Because guys, literally, that's all you need to know is hot things get bigger, cold things get smaller, and less squeezed things get bigger. That's it. That's the review of everything we're going to do for the rest of the day. So the trick is we're going to do it mathematically, and we're going to figure out how much bigger or how much smaller. But that's the summary of the day. So guys, these things have names. So you need to scratch this down, but you guys don't even think of this as your notes, right? Is this notes or is this just something you ignore? Do you ever include it? Okay, so include it. So guys, this is called Charles' Law. So guys, let's review. What do hot gases do? They get bigger. What do small gases do? Or cold gases do? They get smaller. You ready to make that really difficult? That's what this says. The volume of a gas at constant pressure varies directly with Kelvin temperature. That means hot things get big and cold things get small. Sometimes, guys, we try to make things sound sciencey and we just make the obvious difficult. Guys, that's it. All this is saying is things heat up and they get big and things cool down and they get small. So don't get dumber because of your education. You already knew this. If you're not still sure what we're talking about, let me give it to you in arrow form. Ready? Temperature and volume. If something gets hotter, its volume goes up. It gets bigger. If something gets cooler, its volume goes down. It gets smaller. You guys sold on the idea? So here's the interesting question. So what? Well, guys, let me give you some practical applications for this. You ready? Are you guys all caught up? Guys, have you ever had this experience? So frighteningly, for those of you that are taking AP, when I see you again next fall, between now and then, I will have a child with a driver's license. That blows my mind. But my son and I are right now in negotiations. He thinks he should be able to park his car in the garage. My answer is, no chance on earth. You're parking in the driveway, and when it snows, you get to go out and scrape off your windows like I did when I was your age. We're still in negotiations. But guys, have you ever had this experience where if you are a driveway parker and it's probably 30 in the morning and you realize you're not going to make it to school on time, and you open the door and you look out and you're like, oh crap, my car is like entombed in ice. You know what I'm talking? And you got to go out and scrape. And then anyway, so have you ever gone out and looked at your tires on a really cold school day morning? And guys, you've been parked outside and your car is cold and you look at your tires and they look flat. Have any of you had that experience? Guys, do you understand that on a cold morning when your tires look flat, you have not been pranked by one of your friends and they came over and let the air out of your tires? Why do your tires look flat? Okay, so the air inside your tires is cold, and what does Charles' Law say? When a gas gets cold, it gets small. and your tires look flat. So how do you fix the problem? Guys, don't inflate your tires. How do you fix the problem? You drive to school, and as you drive to school, the rubber in your tires flexes, and that causes friction, and that heats up the air inside your tires, and by the time you get to school, your tires are reinflated. See, guys, there wasn't less gas inside your tires. The difference is that your tires look flat because the gas was cold. That's what Charles' law is all about. You get it? So if you understand the cold side of things, talk to me about how this works. How do hot air balloons work? Have any of you been in a hot air balloon? Yeah? Chase, you have? So how do they work? Okay. You're part of the way there. I'm curious to see if you actually saw this. So Chase is right, all right? That they heat up the gas, and as they heat up the gas expands. So why doesn't the balloon pop? Do you know? Did you see it? Do you know? Go ahead, Kim. Not. But the reason that they do it in bits and increments isn't because they're trying to keep the balloon from popping. It's because if they did, they'd end up so high in the air that they couldn't breathe. So they could. So guys, how does this work? Why doesn't the balloon explode? You guys not know? Yeah.
Some of them escapes and also expands.
How does it escape? It does. Guys, and did you see this, Chase? There's actually a trap door in the top of the balloon. And what happens is when the balloon operator pulls the blast furnace to heat up the air, simultaneously they pull on a rope that opens a trap door in the top of the balloon. And as the gas then expands, because it's heating up, as the gas expands, instead of making the balloon bigger, it expands through the opening in the top, and it escapes through the opening. And then when they shut off the burner, they close the flap, and the gas that is still trapped inside the balloon, because it has expanded, is less dense, and that makes the balloon float. But guys, if they didn't have the trap door in the balloon would expand and pop rather than floating, because you need to let that expanding gas out. And so they have the trap door in the top to let the gas out. Did you see that happen? Yeah, it's freaky. I understand that there's that moment that they pull on that, and you can actually see through the top of the balloon into the sky. Did you see that? It was a while, yeah. So, guys, anyway, but again, this is just Charles' law. Heat up the gas it expands, and out it goes. You guys get the idea? Okay, so guys, if that talks about Charles' law, temperature and volume, now we've got to do something called Boyle's law, which is pressure and volume. So guys, it's Boyle's law. Let's make sure you remember the principle. When you squeeze your teddy bear, does it get bigger or smaller? Smaller. That's Boyle's law. Of course, it doesn't have to do with teddy bears. But guys, the principle is the same. When you squeeze something, it gets smaller. So it goes like this. The volume of a gas at constant temperature varies inversely with pressure. And again, guys, that is Boyle's law. But again, we're taking something simple and making it way harder than it needs to be. So let's go back to the teddy bear. When you increase the pressure of the teddy bear by squeezing it more, does it get bigger or smaller? Smaller. And what if you squeeze it less? It gets bigger. So guys, if you like the arrows, it goes like this. If you squeeze something harder, it gets smaller. If you squeeze something less, it gets bigger. That's all there is to it. So guys, let me give you a practical application, actually a couple practical applications for this one. This one's a little more obscure, but let me share this with you. Guys, do any of you know what this is? What is it? Do you not know? It is filled with helium, but who launches these balloons? The Weather Service. Guys, this is what is called a weather balloon. They load these things up with weather sensing instruments, and they send them up almost to the edge of our atmosphere to collect data about our atmosphere. Now, guys, what do you notice about this balloon? It's not very well inflated. Guys, that's on purpose. This bugger's ready to go. They're going to cut these tethers and let that balloon take off. And guys, they purposefully launch these balloons underinflated. Why? Okay, so let's talk about pressure. Less pressure, is that you, KJ? Somebody go with it. Okay, so as the balloon goes up in the atmosphere, what happens to the pressure on the balloon? It decreases, right? Because remember, guys, air pressure, right? And as we move up in the atmosphere, there's less air pressure. So as this balloon goes up, the air pressure on the balloon goes down. So what's going to happen to the gas inside the balloon? It's going to expand and inflate the balloon. So when this balloon gets 10 miles in the air, it will be fully inflated. Not because they're adding gas to the balloon, but because there's less pressure and the balloon inflates. Does that make sense? So guys, what would happen if they fully inflated this balloon and then sent it up? It would explode. It would get up high enough that the balloon would eventually reach that point where the gas had gotten big enough that the balloon fails, it pops, and all of those instruments crash to the ground. You know what I'm saying? So guys, there's actually a really interesting similar experience that maybe some of you have had. Do any of you go in the summer and go up in the Uintas and go camping? Have you ever taken a bag of potato chips with you? Have you ever done this? Do it this summer. Tell your mom and dad that you need to go camping because it's all about science. So guys, go buy a bag of Doritos. And you understand that Doritos are airtight so that the chips can't get stale, right? Take that bag of Doritos and take it up on the Mirror Lake Highway. Have you ever had this experience? What does that balloon, what does that bag look like? Have you seen it? Oh my gosh, that sucker, like you ping it and it sounds like you're hitting like ping. It is so tight, I've actually had them explode. So guys, what's going on? Well, down here in Orem, there's a lot of pressure on that bag and it's not, the gas inside is compressed and it's not very inflated. But you take that balloon up to 10,000 feet on the Mirror Lake Highway, there's less pressure on the chip bag and it inflates to the point where it just might explode. So guys, when you go camping this summer, check it out because it's a very real thing. We've actually had them pop at times. So keep an eye on it. So guys, you understand Boyle's Law? You guys okay? All right. So guys, with all of that done, we understand the principles. Now we need to do it mathematically, and then we're all done, and it sounds like you're leaving. So guys, let's do the math, and then we're going to call it a day. All that you need to do is write down the equation. And so guys, it goes like this. We now need to describe Boyle's and Charles' law mathematically. So we now understand that temperature, that's Charles' law, and pressure, that's Boyle's law, affects the way gases behave. But what does it really change? Well, it changes the volume. So guys, to bring this all together, this is the equation that you need to know. So just write that down, and then we're going to solve it a couple times and give you a chance to do your homework. So all this is, guys, is the mathematical representation of Boyle's and Charles' law. So it's Pi VI over Ti, the I's are initial, and then P final, V final, T final, where the F is the final. So guys, here's the way this is going to go down. Sometimes we'll be changing temperature, sometimes we'll be changing pressure, sometimes we'll be changing both. But this equation will allow us to figure out what that does to volume. And that's how these problems work. So guys, we're going to solve 3 of these. I would encourage you to write down the first one, but not write down the next 2. And then when we're done with these, you'll have a chance to do your homework. So let's try a few. So guys, it reads like this. It says, we collect 75 cubic meters of gas at 25 Celsius. What does the volume of the gas become if we heat it up to 150? So guys, first of all, what does this look like? Well, a cubic meter is a meter by a meter by a meter. So that's a lot of gas, 75 of those. But the gas has a volume of this at 25 degrees Celsius. So if we heat it up to 150 Celsius, what is the gas going to do? Will it get bigger or smaller? Bigger, right? From 25 to 150, the gas is going to get bigger. The question is, how much bigger? And that's what this equation allows us to figure out. So guys, write down the equation with me. PIVI-TI, and then PFVF-TF. And then guys, we've got to figure out what we're changing. So we know the temperature is going from 25 to 150. What's happening to P? What's happening to the pressure? Does it tell us anything? No. So we assume that the pressure is not changing, so we cross it off. Now we plug in what we know. So do we know the initial volume? Yeah, it's 75 cubic meters. Do we know the initial temperature? Yes, it's 25 Celsius. But guys, check this out. You can't use Celsius temperatures. They've got to be Kelvin. So what do? Add 273 and it's 298. Now, looking at the other side, we don't know the final volume. That's our X. But we do know the final temperature. It's 150 plus 273 is 423. Now guys, here's the trick. I don't want to see your math. You should, at this point, be able to solve this. If you're not sure how to solve it, you're going to cross multiply 75 times 423 and then cross multiply 298 divided by X. Then to solve that, you'll divide both sides by 298. Now guys, when you're done with all of that, the answer that you should get is 110 cubic meters. So let me pause for a minute. Let me give you the opportunity to solve this. Make sure you get 110. And by the way, guys, I think the answer is actually 106, but it rounds to 110 because of significant digits. So make sure you can solve this. By the way, guys, why two significant digits? Because here we have 3, here we have 3, here we have 3. So why is it only two significant digits in your answer? Because of the original temperatures. Guys, understand that with temperatures, when you add 273 to those numbers, it doesn't add additional significant digits. So you've got to go back to the original temperatures when you're figuring out significant digits. So guys, if you're not able to get 110 or 106, I'd love to sit down with you individually and help you with that. But are you okay with the problem solving? You guys good? Okay, so let's do two more. But guys, how about if we don't write these down? How about if we just think through how to set them up, and then we'll make sure you can do the math. So guys, try this one on for size. It says we collect 325 milliliters of gas at STP. What is the volume at 167 kilopascals, which is a unit of pressure? Now guys, as you're solving these, you got to write down the equations first, because that will guide the process. All you've got to do is this. You just need to start reading these and plugging things in. So we've got pressure, volume, and temperature. So let's go back to the question. So it says we collect this much gas at STP. What is the volume at this pressure? So guys, what about temperature? Are we changing the temperature? Doesn't tell us anything about temperature, so we just cross that out. So now we know that we're changing the pressure. So we know the initial volume is 325. What is the initial pressure? Standard pressure, which is 101.3, because it tells us that this is at STP. That's standard pressure. So that's 101.3. And then our volume is 325 milliliters. Now we know the final pressure, that's 167. And now our final volume is our X. So now guys, this is even easier to solve. Just multiply these together, divide by 167, and 3 significant digits gives us 197 milliliters, which makes sense because the pressure's going up, so the volume's going down. Yeah?
When pressure goes up, doesn't temperature go up too?
The assumption is that it's being held constant. It is. You put it in something cold, and you suck the heat out. But you're right, if they were both allowed to change, if you increase the pressure, you also increase the temperature. But these, we'll learn about them next year. They're what are called adiabatic systems, which means that their temperature doesn't change. And really what you're doing is just allowing the heat to leak into the surroundings. So, all right, you guys good on the math? All right, one more, guys, and we're done. It says this. If a gas occupies 3 liters at these conditions, what will the volume be at STP? But notice, guys, now we are given a pressure and a temperature. So now we're changing both. So our initial volume is 3 liters. Our initial pressure is 150 kPa. Our initial temperature is 410 Celsius, which we need to convert to Kelvin. So guys, all of that looks like this. Then we want to know the volume at standard temperature and pressure. Standard pressure is 101.3. Standard temperature is 273. And so that looks like this. Now guys, this is where I'm going to sort of cut you loose. The answer to this is 1.8 liters. So if you want to spend a second, run those numbers, make sure you can get 1.8, that's great. Guys, up here on the board is the answers to all of your homework. You've got the homework in front of you, and we've got half an hour to work on this homework. So guys, let's spend this time. Let's see if we can get this homework done. Check your answers as you go. If you need help with the homework or if you need help with the sample problems that have been on the board, please let me know. And guys, I will get back with you in about 20 minutes and talk with you about pride reports and things like that. But spend the time right now and let's get this homework done. So questions about this before I sign off? Okay, so guys, if you need help with anything, let me know. Otherwise, let's get this homework done. Oh, that's not what that was supposed to do. All right.